Welcome everyone to a brand new episode on hyperbolic orbits. Today I have the pleasure of speaking with someone who works as a behavioral economist, and we're going to learn from him a lot about how that connects with nature as well as space. We have with us today Professor Subrato Banerjee, who is currently a faculty member at the Indian Institute of Technology, Bombay, and a behavioral scientist at the Center for Behavioral Economics, Society and Technology at Brisbane. He is an associate editor at Nature for Humanities and Social Sciences Communications and a guest editor at Frontiers in Behavioral Economics. His research interests span behavioral and experimental economics and applied game theory. He writes columns for news publications like the Business Standard, the Indian Express, the Financial Express, the Asia Times in the financial section, and Down to Earth. Professor Banerjee is a member of the Royal Statistical Society and the Economic Science Association. He has taught courses on data analysis, microeconomics, and applied economics at the Queensland University of Technology, and courses on statistics, econometrics, and behavioral economics at the Indian Institute of Management, Indore, and at Shiv Nadar University. His personal interests include astronomy, astrophysics, and Indian classical music. Thank you, Professor Banerjee, for joining us. It's such a pleasure.
It's a pleasure for me as well. Thank you for having me with you.
Thanks a lot. Let's begin by understanding your education. You have a very, very interesting background, and we'd love to know about how it all started and about your career path.
So, the beginning was actually an accident. It's not really that big a surprise. So, I was always interested in mathematics, and I was reasonably good at it, growing up from school. And during my undergraduate days, I had in fact even taken up admission into mathematics honors. This was in Hindu college and right on the first cutoff. So then, once some inquisitive relatives who really wanted to know how I did in my 12th got in touch with me. The first thought was, why take up mathematics honors? Why not economics honors? Because at that point in time, econ honors was the in thing. It was something that saw the surge in demand, which happened almost overnight. And interestingly enough, I was not mature enough at that point in time. Coming out freshly from school, still exploring avenues. And by the way, remember, these are the days before Google. So this was the point in time before I had first used Google. So there was no information, and the only source of information was basically, from immediate family or relatives who were really, really, all of a sudden keen about, how I had done in my 12th. So the word went around that econ honors is the most it's the most sought after course in Delhi University, maybe only second to BCom honors. So why not take one of the two? And then thereafter I have been more or less married to econ since my undergraduate days. So 3 years of undergraduation in Hansraj College, Delhi University, followed by 2 years of post-graduation, masters in economics from JNU. And then I had a very short stint of about 14 months in the corporate world. I kind of enjoyed that as well, but then I realized immediately that it was not my calling. So I got back to academia after I had cleared the entrance for the PhD in economics, for a PhD in quantitative economics at the Indian Statistical Institute, Delhi. And I have been with econ ever since.
That's wonderful to know. That's for the first time, I think we have a guest who admitted that relatives and other people played a role in it. No, but
yes, they were more interested in me in my performance than I myself was back in my 12th grade. So
it does play a role. My backup was actually close to home, studying mathematics at Jadavpur University. Fortunately, my parents let me go ahead with aerospace. But right. It's nice to know that you did your part in the corporate world as well. And then you moved back to academia.
I mean, I had to know what did not work for me. Right? So
yeah, that's important too. So how is the research going? Where did you start? What do you like so much about the research field and economics?
All right. So in economics, as it has been the case in the last few decades, economics is becoming increasingly mathematical, to the extent that it is now today safe to say that mathematics is pretty much the language of economics. And it also explains this growing trend among institutes here in India, um, that have seen a surge of econ departments throughout the country. And IIT Bombay being an example, so the economics department just became a department of economics when it broke off from the larger Department of Humanities and Social Sciences early in 2023. So it's just a 2-year-old department. And with apart from the IIT Bombay, IIT Kanpur had a fully established Department of Economics, and they've had it for a while now. IIT Delhi is another IIT which looks at a formal econ program, and it's a formal postgraduate program at the IIT Delhi. We have an undergraduate degree. It's called the BSc in Econ, and we do offer an honors as well. And uh, and uh, the thing is that I was always interested in quantitative things. I was always interested in mathematics, and once I realized that growing up further into my days of undergraduation, once I realized that okay, mathematics is the language of econ, I became increasingly more and more comfortable with the subject, to the extent of wanting to do research in the long run. And right now, I'm currently so right now I'm working on fields like cooperative game theory, and I do experiments in the laboratory and in the field that essentially look at um, that essentially test the validity of either the axioms or predictions of ideas or theories in econ. And it's kind of exciting because it's upcoming, and not many people. So the behavioral econ uh, uh, culture is kind of catching up here in India, and we also have now conferences that are being organized on a very regular basis. There is one called BREW, like BREW. It stands for Behavioral Research and Economics Workshop. And my colleagues at the IIM Ahmedabad, IIM Bangalore, and some other places, they are JNU. They are actually organizing this conference on a very regular basis, and we've had the good fortune of hosting it at the IIT Bombay as well. So the behavioral econ. So coming to your question now, when I was doing my PhD, behavioral econ still was not very established here in India. But then, because it was something new, because it allowed me to interrogate certain established models, certain established ideas of rationality. I think that's what really got me interested, because I've always been this one person who has a love for fundamentals. And when the fundamentals are not when the fundamentals are themselves questionable, I think that's when we need to interrogate you know everything just a little further. You see where I'm coming from here, right?
Yeah. And what would be, if I ask you that to explain to a layperson what behavioral econ is, the subject that I struggle to pronounce properly so much, what would you say? What does it entire thing entail?
Well, in a nutshell, everything. So, see, the thing is that why do we create models? We try to create models to understand reality, to make a sense of realities, and this is, in some sense, what makes economics closer to a science. We have a model to predict a behavior, and then we basically see some empirical anomalies in uh, in terms of what is predicted and what is observed. And if there's any difference between what is predicted and what is observed, we go back to the blackboard and chalk out a theory that accounts for the new observations. I mean, it kind of explains how Einstein's relativity explain not just Newtonian physics, but a little more. The orbit of Mercury being an example, and that's essentially what to draw a fair analogy, behavioral econ does. So it basically picks up these elements of new classical economics models that are already established and and have essentially stood the test of time empirically slash experimentally. Whenever we see departures, in the experimental laboratory, behavioral economics basically steps in and tries to make those corrections in a way that those corrections are subsumed within the larger framework of neoclassical economics. And the occasional departure is also kind of welcome. And that is essentially, giving you a feel of what I do. Yeah.
And it's also that you mentioned you do have a knack for the skies. I mean, astronomy and astrophysics. Where did that come from?
Well, as a child, I like to say that I was very very curious. The stars always fascinated me, and I have always enjoyed all my visits to different planetariums when I was a child of uh, you know under 10, when I was a child in my teens, and then when I was a child in my 20s, 30s, and so on and so forth.
Right. And that, if I understand correctly, so your work spans, like you said, literally everything. It involves nature. It could be extrapolated to the skies.
Mhm.
And the since you talked about telescope, you have a telescope, right, that you use on.
So I did have a telescope when I was living in Brisbane. Our colleagues had gifted it, and I remember being making the best use of the southern hemisphere skies, which are, by the way, on an average cleaner than the northern hemisphere skies. And immediately after dinner, just walking out to my front yard, placing the telescope, and then looking at the Galilean moons of Jupiter, the rings of Saturn, the craters on the moon, and then use the Barlow magnification lenses to look at the craters within the craters, and it took a few photographs here and there. Often the view of Mars, the view of Venus, was spectacular, and then, I mean, of course, a few things here and there in the night sky. It is always fascinating.
It is. And recently, this mission that we had, JWST, James Webb Space
Mhm.
Telescope, it is not only like in it's engineering wise, science wise, in all phases, it has crossed, I think, boundaries in all sorts of dimensions. There is a beautiful documentary on it also on Netflix that I've seen multiple times. And
What's
it's,
it called? I'm curious.
I think it's called The Unknown
Okay.
Cosmic Machine, something like this. It's a wonderful documentary. It's very close to being my favorite after the one that did on black hole imaging, when they imaged the first black hole.
I'm
And
writing it down.
it's they have shown how difficult it was for them, not too much of the design phase,
Mhm.
but the operations phase too, that they had over 300 single point failures. If any one of them had faltered at millions of kilometers away from Earth, they would have failed. And they had a bad experience with the first time with Hubble,
Mhm.
with the mirror not being perfectly polished. And so this time they were extremely careful. You must watch that documentary. It's lovely.
Okay, thanks for recommending it. Yeah, I'll be on it immediately after this. Yeah.
Great. So why I mentioned this is that is the design of that entire mirror. They wanted to capture light. They wanted to go back farther than Hubble did. That
Mhm.
they wanted to view the universe as it was millions of years after the Big Bang, and so they needed a huge reflective surface.
Mhm.
And the problem was never science. The problem is engineering needs to catch up. So the rocket fairings are too short, and they don't have enough space for that huge thing to put. So what they did was they took inspiration from beehives.
Mhm.
Beehives use these compact hexagonal things, and they have put 18, if I'm not wrong, 18 different elements of that mirror put together
Mhm.
in hexagonal shapes, so that There's also a thing of redundancy in space missions, that if any one material or part that something goes wrong with it, it should not affect the
Yeah,
others.
yes.
And they have managed to do this in space. They have operated it and it's successful. It just blows my mind sometimes.
Well, it's an optimization problem that honeybees really got right. And I mean, what are the two basic necessities for us to survive? Food and shelter. Food is the most obvious thing, and shelter, again, the second most obvious thing. So honeybees really had to solve this problem. I mean, of course, they had millions of years to solve it and get it right. I mean, unlike in the case of us human beings who just have to attend a lecture by Johannes Kepler, who was kind of interested in these stacking problems. Of course, I'm joking. I never attended lectures by Johannes Kepler. But then these are interesting problems, and these are also timeless problems, because it's not just us um, who needed to solve these problems, like in the case of the telescope that you mentioned. But honeybees had to solve this problem. They had to get it right, because it's a very real problem of space management. And it's a two-stage optimization problem. I mean, if you really look at it, no other shape but the hexagon would have worked. I'm actually happy to share some slides, and maybe put this across. Can
Yes,
I try?
please.
Right. So, let's think of the most basic, the most godly figure, if you will, in two dimensions, and it has to be the circle. And now, I mean, think about the problem that really a variant of the problem that really interested Johannes Kepler. He was really interested in stacking up spheres of like size. But then, instead of thinking in three dimensions, let us simplify matters a little bit and think about two dimensions. So let's think about the most quote unquote perfect image in two dimensions, and it has to be the circle. It's the most godly, to the extent that it kind of perturbed, a lot of explorers, erstwhile explorers, who dared look up to the night sky, to the extent of not being to the extent of being dissatisfied with the very thought that the planets did not assume orbits that were circular, but were elliptical instead. So perfect is the image of the circle that if God were to step in and design the universe, everything had to be circular, almost as a first instinct. But then let's come back to this problem, and let's try and ask a very fundamental problem. I mean, suppose you've been given a circle of, suppose you have a circle of a given size. Now, how many circles of like size, how many circles of the exact same radius and therefore area can you really surround this original circle with? So there, I have that initial circle. Can you see that?
Yes, yes.
Yeah, okay. So that circle, it's purple in color, and I have that circle. Now the question is, how many circles of the exact same size can I surround this original circle with? And what do you think is the answer? Oh God, I've already given the answer.
Yes, it's on the slide.
Yeah, it is on this slide. So these are the 6 circles of like size. Believe me, they're the same size. I mean, I know that because I'm the one who copied and pasted them without making any alterations. So you'll immediately see that the answer is 6. You can surround an original circle of a given size with exactly 6 circles, with a maximum of exactly 6 circles of the exact same size. Now, the question is, why is that? And before I even get there, can you see my cursor? Do you see these gaps in between?
Yes, yes.
The white gaps between the pink surrounding circles and the original purple circle. And the point is that the gaps in the middle are basically a source of inefficiency. I don't want those gaps. I want to avoid those gaps to the best extent possible. But I'll come to that in a while. Let me just address the first question: why 6? It's easy to see that if you were to join the centers of all the adjacent circles with each other, you will get this perfectly shaped hexagon. This is a regular hexagon right in front of you. And a regular hexagon is nothing but six equilateral triangles stacked up together. You see these six equilateral triangles stacked up across two dimensions to form a neat hexagon. And all that you need to do is join the centers of all the adjacent circles to the center of the circle, the original circle in between. But here's the beauty of this argument. You can actually extend this argument individually for each of the surrounding circles. So you pick up, let's say, this circle here. I can think of this circle to be at the center of six other circles of the exact same size. So the three original circles. So there are these three original circles here. And then I can add three more circles that surround this circle here, this adjacent circle here. And if I were to do that, this is what it's going to look like. I'm not making the circles, but it's kind of easy to imagine those circles. All that you need to do is you just have to put circles at the centers or at the vertices, circles with their centers at the vertices of these regular hexagons. And it turns out that I can go on doing this. I can actually go on doing this in a way that no gaps are left in between any two shapes. Now the question is, does this image look familiar?
Yes.
Okay. This is what this image likely reminds you of, at least as a first instinct. Now, honeybees are, as it turns out, very good, extremely good architects, actually. And those little cells there, those are as good as perfect hexagons. And what's the degree of accuracy? How does it compare with the tolerance for inaccuracies that we human beings have? Just to make a simple comparison, you will find this comparison in the book called Scarcity. It's a book titled Scarcity by it's authored by Senthil Mullainathan and Eldar Shafir. Two brilliant people in the field, and they basically talk about why this is actually a problem of economics, literally a problem of space management, where you're weighing marginal benefits to marginal costs. So these are perfect hexagons of wax with a wall thickness of less than 0.1 millimeters. And if you look at the standard deviation figure, you're basically looking at a 2% tolerance level. How does that compare with the National Institute of Standards and Technology? We apply a 10% tolerance rule in the construction of plywood. So let's just say that let's just say that honeybees are more intolerant to errors than we human beings are. Now, what is it that makes it all the more remarkable? They actually do this locally. So unlike in the case of all human constructions, there's no blueprint. There's no chart for honeybees that says that this is what the final structure should really look like. They all basically are happy to work locally, and what they do is they flap their wings to generate adequate heat between their bodies, and they basically mold the wax to produce all these cells locally, and they do this in complete darkness. If you don't think that itself was not remarkable enough in its own right. Now the question is, where does the wax really come from? Well, the answer is very simple. They poop it out after consuming honey, and the exchange rate is exceedingly steep. So let's just say that 8 pounds of honey consumption actually translates to 1 pound of wax that actually goes into the construction of beehives. And to collect all that wax, any guesses on how many individual honeybee trips are needed?
No idea. No.
About 80,000 to 90,000 honeybee trips, to and from the place where the beehive is supposed to be, and the flowers. So 80,000 individual honeybee trips. That's quite the number, and a lot of honeybee hours, if you will. a lot of honeybee hours. And the bottom line being that, if you really want real estate, you have to work hard for it. Something that we humans can really, really relate with. So now the question is, what is it that made the honeybees really get it right? You know, why did they? Why is it that they were forced to get it right? Now, if you think of it, the input that actually goes into creating this huge hive, um, it's actually an economically scarce resource. So 8 pounds of honey gets converted into 1 pound of usable wax that goes into the construction of this hive. And this hive is important because not only it gives them shelter, they get to store their food, they get to store honey, they get to take care of their young ones, the next generation. And the hive itself is like it's like this huge macro organism in its own right, if you will. And if you really think about it, it's a complex it's a complex mechanism that unfolds in front of our eyes. Now these are little characters that really need to get it right, because the input that actually goes into creating this beehive, it's a scarce economic resource. So space is scarce. Now the question is that given scarcity in space, what is the best that you could really do? Now, what is the best that you could really do? Turns out that the answer to this question is that it's the regular hexagon that actually solves this two-stage optimization problem. I'll come to the two stages in a while, but let's compare that to what a close cousin of the honeybee, in this case the mud dauber wasps. What kind of a problem what kind of a space problem do these guys really face? So if you look at this image here, this is this is an image of a nest of the mud dauber wasp, and it literally uses mud to create its nests. And you'll immediately see that this is an image that doesn't have any specific structure. And the reason is because they don't really need to worry about the structure. Mud is an economically abundant resource, so the cost of obtaining mud is relatively low. So they don't really have to worry too much about getting it right. They really don't have to worry too much about that perfect shape for a nest. They're happy to, since the input that goes into manufacturing or creating this house is an economically abundant input, they don't really have to worry too much about getting the structure right. So that's what it really looks like, and that's the problem of the honeybees. Now the question is, why did the honeybees have to get it right? Well, the answer is very simple. At some level, honeybees and mud dauber wasps, they just behave like us, during two different they behave like how we would behave under two different scenarios. So imagine that you're actually going on a holiday, and in the first case you have a small suitcase to pack, and in the second case you actually have a large suitcase to pack. Now here's a question: when will your packing be more careful?
The small suitcase, definitely.
Absolutely. So, I mean, so when you have very little space, when space is a very real economic constraint, what is happening here is that every time you plan to put something in it, you're forced to think what should go out, what should come out of it. And then there's this question of, uh, weighing the benefits, at the margin. Let's assume for the moment that you don't have a lot of space left after you've, more or less filled up your small suitcase to the brim. And when you're already done, you kind of feel that, okay, there's something else that you want to carry, but then if you were to put that inside the small suitcase, something else should come out. And then it's just a question of, the relative importance, the relative benefits of carrying this additional item vis-a-vis another item that is already in the suitcase that must be taken out to accommodate for this. So at some level, you're already behaving like an economist here. You wouldn't really have to worry about getting the packing right when your suitcase is large enough. So when in fact space is no longer a real economic constraint. And turns out that honeybees behave uh, in a way that we would actually behave if our suitcases were small. And mud dauber wasps would actually end up behaving in a way uh, that we would behave if our suitcases were large enough. So let's look at why hexagons. Let's look at to even begin answering this question, let's look at some counterfactuals. What if it is not a perfect hexagon? How about a perfect square, on the right panel, and a perfect pentagon on the left panel? Now, the question is, think of these as individual cells, one with five walls of equal size, and the other with four walls. Now, the question is, can I add another cell adjacent to each? The answer to that question is yes, I can. It's possible for me to do that. Now the question is, can I add a third cell that is adjacent? And the answer is yes. But now the next question is, can I add a fourth cell? What do you think is the answer? Can I add a fourth cell of like size for the regular pentagon?
No.
No, I can't. But can I do that for the square?
Yeah.
Yes, I can do that. And the thing is that I can't add a fourth cell because you see that little slice, that yellow slice, that is a measure of inefficiency. It's like a gap that I'm leaving, like I did, with these white regions between, two adjacent circles. Circle is just like another shape. The circle is just another shape, just like the the square and the pentagon. And it turns out that I can't do that because the common angle of a regular pentagon is 108 degrees. Okay, so I've put this little circle right at the center of both these images. You can see that, right? Yeah.
Yes.
Yeah. Now, what happens is that, once I have put in, once I've stacked up three regular pentagons, so the angles, the individual common angles add up to 108 plus 108 plus 108, making it 324 degrees, which gives you the slice of 36 degrees, a residual of 36 degrees that could have gone into complete the circle, complete all the 360 degrees that are available. Right now, as it turns out, that is not a problem with the perfect square, because the common angle for a perfect square is just 90 degrees, and 90 degrees divides 360 degrees exactly. So you have 490-degree angles that make up that 360 degrees. So clearly, a square is a good candidate, but then a regular pentagon isn't. So the question is, what are the other likely candidates that, quote unquote, leave no slice in between? What are the candidates that essentially have a common angle which divide 360 degrees exactly? Right. So now it's just a question of finding out the factors of 360 degrees. So let's look at 90 degrees is right here in front of you. 108 degrees isn't a factor of 360 degrees. How about 60 degrees? Yeah. So 6 equilateral triangles stacked up together. They will again leave no yellow slice in between. How about a regular hexagon?
The solution to the problem.
Yes, so it's one of the candidates yet. I mean, I haven't said that this is the candidate that uniquely solves the problem. So it is one of the candidates because it has a common angle of 120 degrees, which again exactly divides 360 degrees. I mean, if you were to look at any hexagon here, yeah, think of drawing a circle. Think of drawing a circle here, and you will see exactly three hexagons with angles adding up to 360 degrees. That's thrice of 120 degrees. So it turns out that the only candidates that we have are the regular hexagon, the square, and the equilateral triangle. The equilateral triangle, again, I have already talked about it before. So think of the circle, the original circle as the circle, and all the 360 degrees basically get divided into 6 equal slices of 60 degrees each. And you can easily see that the equilateral triangle also solves the problem. So now the question is very simple. We only have 3 candidates: the equilateral triangle, the square, and the regular hexagon. So out of these 3 candidates that leave no space in between, that leave no unused space or unused slice in between, which is the one that needs to be picked up? So for that, we need to look at a slightly different problem. Okay, once we know that these are the only 3 permissible candidates, we just have to look at one mathematical result, which I have highlighted here. If you just look at the last sentence in this slide, for a given perimeter, the area increases with the number of sides. So imagine a thought experiment where you initially begin with an equilateral triangle, and then you add sides. You basically keep on adding sides. So think of the equilateral triangle, which is a regular polygon with 3 sides. Think of the square, which is a regular polygon with 4 sides. Think of the pentagon, a regular pentagon with 5 sides, a regular hexagon with 6 sides, and so on and so forth. You will immediately see that for a given perimeter, the greater the number of sides a regular polygon has, the greater is the area. And in fact, think of a regular polygon that have let's say 10,000 sides. You will not be able to, at least from a distance, distinguish it from a square. From a circle. You will not be able to distinguish it from a circle. It is as good as a circle, and it is immediately observed that the greater the number of sides, the greater is the area. And the limiting value is in fact the value of the area of the circle, in this case pi r squared. So in fact, the circle is the most it's the most efficient way of using whatever material you have to build a wall, so that the area within it is the maximum. But the point is that a circle is not permissible, because you can't make cells out of the circle. They will leave those white gaps in between. Okay, so now we have 2 results here. The first is, the greater for any given perimeter, the greater the number of sides, the greater the area. The greater the number of sides, the greater is the area. And now we only have 3 candidates, as we argued earlier on. We have the equilateral triangle, we have the square, and we have the regular hexagon. The question is, out of these 3 shapes that do not leave any inefficient gaps in between, which is the shape that gives me the maximum area? It's the hexagon. So it's a 2-stage optimization problem. In the first case, you want to minimize. In the first stage, you want to minimize any residual gaps between 2 adjacent cells. All right, and subject to that constraint, subject to that requirement, the next question is, what's the best that you can do in terms of a given perimeter, and what's the best that you can do in terms of maximizing area for a given perimeter? So it turns out that it is the regular hexagon that uniquely solves this 2-stage optimization problem. And it's a beautiful problem that honeybees were kind of forced to solve. I mean, again, not that they've attended classes by Johannes Kepler or taken elementary lessons in Euclidean geometry, but this is one of those rare examples where nature really, really had to get it right, at least for the sake of honeybees. So honeybees have actually solved the shelter problem. I mean, of course, they had eons to solve this problem, and the ones that did basically survived precisely because they had good shelter.
First of all, this is a very beautiful presentation.
Thanks.
We are seeing a lot of bio-inspired designs in every field. And this is one case where nature has got things correct.
Yes.
and has taught us how to do things correctly.
Yeah.
But is there any example or instance where, you know, things may have changed in our surroundings very rapidly and nature may not have caught up so easily? Is there a possible example of that?
Well, yes. Turns out that the answer to that question is also yes. So just like us human beings, nature is also on a learning spree, if you will. Um, I mean, I wouldn't really say that nature got it wrong, but it's just that you know, once you've solved a problem, and if the original parameters of the model change, then it is not necessary that the existing solution will still continue to solve the problem. Let me put it that way. A very simple example of this in Econ 101 is, the standard demand and supply model. We have what is known as the law of demand, which in English says that, the greater the price of something, the higher the price of something, the lower is your willingness to buy it. And then you have the law of supply. The greater the price of something, the more you're willing to sell it. And you basically have that downward sloping demand curve and upward sloping demand curve. They intersect at what is known as the equilibrium price. Now, what happens is that the equilibrium price is the solution to the allocation problem. It's a solution to the allocation problem, in the following sense. It basically asks at what price there is no excess residual demand, and at what price there is no excess supply. And turns out that the price at which both these problems are balanced out is unique, and at least in the standard simplified framework. Now, suppose the thing is that, if there are immigrants, let's say, in a given locality, obviously now there are more buyers because they can't, sell things overnight. Let's just say that there's this surge of immigrants, so the demand curve actually shifts outward. You will see that the original equilibrium price will no longer solve the problem of market allocation. So effectively, what I'm saying is that the original solution that was arrived at will no longer work. And it turns out that the story of moths, the story of moths actually is an example of where, nature got it right, in a world where artificial lights were not the norm. And once artificial lights came about, the original parameters of the model essentially changed. So the heuristic that was evolved to navigate, no longer works. So here's, by the way, an image, and you can easily chart out the spiral path of moths that are essentially being driven to this lamppost here. And it's easy to chart it out, and it's also easy to write down the set of differential equations that exactly characterize the path of any given agent here. Now the question is, are they really trying to commit suicide? So imagine, you're having dinner, and right in the middle of dinner there's a power cut, and there's nothing you can do about it. Now, obviously, you'd want to see what you're eating, so you light a candle, and then let's say 5 minutes further into your dinner, you see all these annoying moths being attracted to light, and essentially giving you the impression that they're trying to commit suicide. Well, turns out that they're not trying to commit suicide, as many poets will have you believe. No, that's not the purpose, because let's just face it, there's no survival advantage in killing yourselves. Okay, so no, they are not trying to commit suicide. What is happening here is essentially a side effect, if you will, of an evolutionary conditioning that worked for moths in a world, or on a planet that did not have nearby sources of light. The question is, how old do you think is the oldest lamppost ever? 200 years, 250 years tops, not more than that. you know uh, so 200 years or 250 years is just like a blink of an eye in geological time scales. What I'm trying to get at here is that, uh, moths have not had the time to evolve a heuristic that accounts, a navigation heuristic that accounts for sources of light that are very, very close to it. So let's look at the, let's look at how this heuristic really works. So imagine driving in the evening on a straight road, and while you're driving out, let's say from A to B, you see this distant person who's waving at you, this orange distant person who's smiling at you, and he's waving at you. So you're driving on a straight road, and you basically see that person at a distance. And then let's just say for some reason there's this person who basically, this yellow guy who stands right in the middle of the two of you, essentially blocking your view. All right. So you end up waving not to the distant person, but the nearby person. Now, since this person is blocking your view, it must mean that this person is actually making the exact same angle with respect to where you are and the direction where you're heading. So let's just say that A is the position of your car. So when you're driving, you've reached position A and you're driving towards B, and the nearby person is essentially blocking your view. You can no longer wave at the distant person. But what happens is that when you travel a little further from A to A prime, you'll immediately see that now it's possible for you to tell apart the nearby person from the distant person. In fact, you can simultaneously wave at both. And the question is, what is happening here? Well, the reason why this happens is because the angle relative to the person who's nearby is changing faster than the angle with respect to the distant person here. So if you were to if you were to drive your car and wave at both of them, one person being nearby, the other person being at a distance right behind this nearby person, if you just travel a little further ahead, you can tell them both apart, simply because the angles have changed. You can simultaneously wave at both of them, or maybe you could sequentially wave at the nearby person first and then wave at the distant person. So what happens here is that when you're driving, or if you're being driven, and if you are on the window seat, nearby objects will typically if your eyes are fixated on nearby objects, they will actually force you to turn your head very quickly. Like in this example, when you're going from A to A prime, when you're looking at a person who's nearby, when you're driving, your head literally moves like that, very, very quickly. But if it's a distant person or a distant object, let's think of let's think of a tree that is far enough out there. You will immediately see that the angle changes very, very slowly. So you're driving your car and you look at that tree at a distance, and from this distance, you'll realize that you're actually changing your head very, 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 very slowly. Word of caution here, please don't do this when you're actually driving. Only do this when you're being driven and you're on the passenger seat by the window. Okay, so with that disclaimer out, it's easy to see now that the angle with respect to the distant person will change relatively less than the angle with respect to the nearby person. Now, have you ever felt that the moon is traveling with you, when you're traveling on the straight line?
Yes,
On a
as a
straight line?
child, I still
Yeah.
do. In fact, yeah.
You still do? Well, the reason for that is because the moon is at a practically infinite distance, and so what I'm basically saying here is that because of the fact that it is at a practically infinite distance, the moon is obviously farther than the farthest tree that you can see when you're being driven. You see what I'm saying, right? So if the moon is farther to practically at an practically at a great distance away, it kind of gives you the what is essentially happening here is that when you're going from A to A prime, the angle that you're making relative to the moon changes very, very very, very slowly. The change in the angle is minuscule. It is not as drastic as the change in the angle from A to A prime for the nearby person. essentially what is happening is that, since this angle more or less remains a constant, it gives you the feeling that the moon is traveling with you as you're going from A to B. Yeah. So you're driving on this straight road and you're looking at the beautiful moon in the evening, and you go a little further, it gives you the impression that the moon has also traveled with you, simply because of the fact that the angle relative to the moon has not changed. At least it has not changed significantly. The change in angle is minuscule to, to the extent of being imperceptible by us. Now it turns out that there's a corollary to this result, and the corollary is thus. It follows thus. Um, the corollary is that if you maintain a common acute angle, no matter what the acute angle is, could be 30 degrees, could be 45 degrees, could be 60 degrees. If you maintain a constant acute angle with respect to a celestial object, a celestial body, then it helps you travel on a straight path. Do you see that? I mean, it's kind of easy to see, right? If you maintain a common acute angle with respect to a celestial body, it kind of helps you navigate in straight lines. And by the way, navigation in straight lines is the most efficient way to get from A to B. So if you have to go from A to B, the shortest distance is, the straight line that connects point A to point B. Traveling on straight lines is efficient. Now the question is, um, does this heuristic necessarily fail in a world where an agent, in this case the moth, cannot distinguish between a nearby source of light from a far enough source of light? Let's just face it, 200 years again is a blink of an eye, like I said earlier, in geological time scales. So moths have not had the time to account for nearby sources of light. So any source of light is as good as the moon. It treats it as light coming from the moon, and it tries to maintain an acute angle so that it can travel most efficiently in straight lines. Now the question is, why is travel important? Well, moths are migratory insects, and turns out that migration itself has an evolutionary advantage. Imagine a tree, an ancient tree with two branches, one branch with a nest of a moth that did not migrate or have the ability to migrate or move around, and the other branch, with a nest of a moth that had the ability to migrate or move around. Now there's a forest fire. Which one do you think has an evolutionary advantage? I think the answer to that question is immediate. Uh, so migration itself has an evolutionary advantage. The ability to migrate itself has an evolutionary advantage. Now the question is, okay, if you have the ability to migrate, how do you migrate in the most efficient manner? And it turns out that you would want to travel in straight lines as much as possible, because that's the most efficient way to travel. At least in 2 dimensions, this argument is easy to see. And one heuristic that moths have evolved. So moths um, have evolved this one heuristic which allows them to travel in to travel on straight lines. And the heuristic is very simple. All that they need to do is maintain a common acute angle with respect to a celestial object. Now the question is, what happens when the moth cannot tell apart if the source of light is near or far? So suppose the moth wants to go from A to B, and there's this nearby source of light, but the moth thinks that it is actually as far as the moon is, and it wants to maintain a common acute angle, let's say 30 degrees, with respect to this nearby source of light. So let's imagine the trajectory of the moth that wants to maintain a common acute angle with respect to this nearby source of light. So let's just say that it travels from A to A prime, and it immediately sees that the angle has changed drastically simply because the light is nearby. Just like, how I would turn my head if I were to look out of the window at an object that is very near to me. Okay, that's exactly what is happening to the moth. The moth is traveling from A to B. It's traveling towards the direction of B. When it travels a little further from A to A prime, it actually sees that the angle has increased drastically, from 30 degrees. Let's just say that it's close to, how much do you think is that angle? 55 degrees? 50 degrees? I don't know.
About that.
Yeah, about that. Okay. So now the thing is that the moth says to itself, let's dramatize this a little bit, okay? So the moth says to itself, hey, you know what? I was trying to maintain an angle of 30 degrees, but then as I'm traveling towards B, this angle is increased, and this has never happened to me before. The moon is so well behaved; it always travels with me. Whenever I want to maintain a common angle and travel on straight lines, what has happened here? Okay, let me try and reduce this angle back to 30 degrees. Maybe I need to make a course correction here. And that's exactly what the moth does, because it's been programmed to maintain that common acute angle so that it could travel on straight lines in a world where there are no artificial sources of light. So at A prime, it decides to make a course correction and reduce that angle back to 30 degrees by turning slightly left. And this is what it does. So now instead of heading towards B, if it heads towards B prime, you will see that it has reduced the angle back to 30 degrees with respect to the nearby light source. Okay, so now the moth is finally happy at A prime. It has made that course correction and it's now traveling towards B prime. The moth thinks to itself, again, to dramatize things a little bit. Okay, I've done the smart thing by making this course correction. But then something interesting happens as it travels further. The exact same argument that I had established before. When it travels a little further on the new path towards B prime, it travels from A prime to A double prime, and it sees that the angle has increased substantially yet again. From, let's say, in this case, from 30 degrees to, let's say, 50 degrees or 60 degrees, or probably 70 degrees in this case. I think it's a little higher than that. So it has to make a course correction yet again to reduce that angle back to 30 degrees. So it turns a slight left, and now in doing so, it is no longer traveling towards B prime, but it's now traveling towards B double prime. And as it turns out, it is very easy to chart the path of the moth, okay, which is trying to maintain a constant acute angle with respect to a source of light. And you will immediately see that this is the path that leads it naturally to the source of the light itself. And explaining why, you apparently end up concluding that it's trying to commit suicide. And it literally takes that adventurous spiral route towards the center, the source of the light, in this case, the burning candle, in the middle of your candlelight dinner. The moth is not trying to commit suicide. It's just that a heuristic that worked in a world where there were no artificial sources of light no longer works in the man's world. And a consequence of this is that, it's a solution that was perfectly suitable for one world that is, in fact, that turns out to be lethal for it turns out to be lethal for another world where we've set up artificial sources of light. So the moth is, again, not trying to commit suicide. It's just consequence of an evolutionary programming that leads it to apparently kill itself, as unfortunate as it sounds.
The most of the conversations that I'm having nowadays, now that I'm doing space education so actively, is that I'm trying to speak to people from various disciplines and tell them that whatever you do in your own field is something that is also done in space. Space is not something, outer space is out of Earth, but the people who work in the space industry do the exact same things that you are doing, just the application environment is different.
Sure.
The way you were explaining, believe me, you were speaking like a space engineer, probably in a design review or that review that happens before the launch, where they decide, okay, this needs to go on the rocket, this does not go because it's taking up too much space, this needs to be folded, this propulsion system is useless, this one is great. It's this optimization problem, because
that is econ 101, by the way. Yeah.
Yeah, we need to think about including these courses more into these kind of engineering or science courses that are more closely aligned with space. Because what happens is we do study maybe aerospace or maybe electronics or mechanical, and we skip out these things and we go out to the real world and see that, well, we have to study systems engineering now, part of which is business and
Well,
econ, like you said.
welcome to the world. Welcome to the real world.
Yeah,
Um,
and
yeah.
even the Moths navigation problem that you talked about, you were speaking like this GNC engineer on a space mission who has to maintain the flight path angle, or the way you were talking that, if you keep your angle correct with respect to a celestial body, you will be able to maintain your flight path.
Yeah. Yeah.
That's precisely what the GNC system or ADCS system does. It has sun sensors and earth sensors and star trackers doing the exact same things. So I can't thank you enough for this presentation, because it's this linking that space is not different from what we do here. It's just an application. So thanks a
Well,
lot for that.
that's a fair point, and my favorite author, Carl Sagan, basically, uh, talks about it in a chapter titled "Shores of the Cosmic Ocean." We've always been explorers at heart, and if you really ask me who a scientist is, I think it's a child that is not outgrown curiosity. And at some level, then we're all children, and we're all children of curiosity. And uh, and uh, the language of mathematics is essentially the same. It's just the applications that are different, exactly as you put it so eloquently. In fact, I was planning to write that down. The point is that the language of mathematics is the same. It's the same language that talks to you, whether or not you're an economist, or a space scientist or a theoretical physicist. Sadly enough, it's all becoming more driven towards application, and I'm not sure if that's a trend that I would want to observe. I think knowledge is always for its own sake, and at some level, that kind of makes me a bit of a theorist at heart. I mean, if you really think about it, it was Aristarchus who actually postulated. He was the first to postulate that stars were essentially distant suns, and it was only much much later, than his time, that we actually understood that that was indeed the truth. That was indeed the case. But before then, nonetheless, stars, without knowing what they were. Uh, Without us knowing what they were, stars continued to solve certain essential problems, problems in navigation, for instance. Problems in navigation. And once we use the stars for navigating our way into new lands, we discovered, different kinds of lands. And that was the birth of, topography. That is the birth of geography, right? So, most of the learnings have actually happened only when we dared to learn, only when we remained curious. Helium, we figured out that helium is, of course, named after the god of the sun god, Helios, right? And we found out helium on the surf. We postulated helium on the sun before we could even guess that it's available on our own planet, right? So I think you're absolutely right when you say that it's the same language. It's just the applications are different. But when you say that, I will add that it shouldn't just be about the application, economics or astrophysics or navigation. I think it should be about the beauty of learning and evolving the language itself in its own right.
Absolutely, I agree. It's the knowledge, like you said, it's for its own sake. I
Yeah.
don't think people 100 years or even 200 years ago, they even thought that there would be so many different disciplines.
Yeah.
Sometimes I feel
It
if
was
you
all
don't,
philosophy.
yeah, it's all philosophy, and everything we do is
Alchemy and
probably
chemistry were the same. Astrology and astronomy were the same. As unfortunate as that sounds, by the way.
yeah, it will raise questions, I'm sure. But then the concept, I think there's too many disciplines and too many categories happen just because we want to keep our school systems simpler. And I do have a question on this. Since you do interact with bright minds on a regular basis, thanks to your
Mhm.
work, so what is the situation with the current generation of students? Are they inclined towards basic sciences and mathematics, or does it not interest them that much?
Okay, so that's a deep question, actually. So when it comes to an approach to education, I will have to say that the crowd here hasn't really evolved much. The reason why somebody doesn't want to engage with, let's say, something like pure mathematics or theoretical physics, and indeed, as we see, the fundings for these areas are actually on a downward, dare I use the word spiral. um, you know uh, the fact is that the reason why people are no longer engaging with these fields is actually not significantly different from the reason why not many people wanted to become cricketers, during our generation or generation before that. And the underlying idea that unifies this aversion in both these areas um, is a certain level of risk aversion. I mean, if you are spending all that time in cricket, playing cricket, there's no guarantee that you'll make it to the top 11, essentially representing the country. And the exact same thing is kind of happening with fields like pure mathematics and theoretical physics, where the amount of funding that was dedicated to these fields has actually fallen down substantially, to the extent that it is, you being a theoretical physics is equivalent to being one of the 10 people who represent the country in theoretical physics. The cricket team only has 11 members. You see what I'm saying? And it's a similar kind of aversion that is leading people to avoid the courses that are quote unquote non-marketable. And I'm not sure if that's a very good very good trend. I mean, if you really think about it, MBA is the in thing, and everybody wants to do an MBA. Little do people realize that not everybody can be leaders. Not everybody is a leader, and you can't beat leadership into people over 2 years of an MBA program. Let's face it. I'm happy to not be a leader so long as I'm contributing in whatever meaningful way I can. Sitting in my little desk here. And at some level, therefore, I am a bit of a Puritan, because all our learning, uh, so think of all the learning that we've accumulated over eons of human existence. I mean, our species is about, I think, what, 100,000 to 200,000 years old. I'll give you 100,000 years. Let's just think of a relatively younger species, and whatever little learning that we have acquired in these years, the best learning actually came when we weren't really thinking of any obvious or any immediate use of any particular learning. Think about the Riemann's formalization of curved space, the geometry of curved spaces. At that point in time, it was known as the weird geometry. But then, 30 years down the line, or 40 years down the line, it proved to be pretty useful for the formalization of Albert Einstein's relativity, who, as a consequence, also thought of the idea of time dilation, which you need to account for, when you're thinking about coordinating your visit from the surface of the Earth towards the International Space Station. Now, interestingly enough, Riemann never lived to see the fruits of his weird geometry in the form of Albert Einstein's relativity, and Albert Einstein never lived to see the first International Space Station. Stephen Hawking, who contributed a great deal to our understanding of black holes, never lived to see the first image of the black hole, which was kind of revealed to the world sometime in the middle of 2019, and we lost Stephen Hawking on March 14th, 2018. At some level, therefore, when you are a person uh, in academia, or if you are a person who's even remotely close to the sciences, you are kind of a brief candle in this cosmic dark, meaning that uh, you're incrementally adding to the knowledge of that humanity already has. And it doesn't have to be substantial, but it has to be knowledge for its own sake, because otherwise, if you're only attaching objectives, specific objectives to why certain knowledges, certain kinds, certain forms of knowledge is acquired, then we are actually making way for what Carl Sagan called a combustible mix of scientific ignorance in a world that is increasingly dependent on science and technology. It also explains why when Arthur Eddington back in 1919 did his gravitational lensing experiment. It got published in Nature on November 6th, 1919. He did the experiment in the month of May. And the next day, it was actually, front page news in a lot of national dailies. Um, uh, Move forward 100 years, and the episode of the Higgs boson during mid 2012. This is July 2012, and the news did not the news of the discovery of the God particle didn't make it to a lot of national dailies, let alone the front page. So something has actually happened to scientific readership. Something has happened to curiosity, in these intervening 100 years. And sadly enough, it takes hits like the Big Bang Theory to make sciences look cooler. But the fact that you need a sitcom to make sciences look cooler, where sciences are no longer cool for its own sake, that itself is a problematic society that we are kind of fundamentally living in. It's a miasma of intellectual deficiency that we are kind of making way for, and I'm not sure if I'm very happy about it. It's a kind of a sad spectacle, because hey, let's admit it, science is cool.
It is. But I have been fortunate to study bachelor's in India, and I did the later part of my studies outside India.
Mhm.
And a major difference that I saw is that the reason that we were so forced kind of by the society to get inclined towards an engineering degree followed by an MBA degree, especially when I was studying, it was the main idea that you will get an IT company, highly well-paid, secure job at the end of your degree. That was
Yes,
it.
you're reacting to incentives. Yeah.
Yes. And then very recently, we also had I'm not going to mention the exact name of the institution, but we had an incident where students were not so interested in working in space because they were comparing. And this is something that I get this question on a regular basis, that
Mhm.
aerospace is not paying as much as
An
the
MBA.
other industries. Yeah. And but the understanding that aerospace is a field that it's shiny, it's great, but it also extremely complex. It needs a lot of understanding of complex mathematics and physics. Now, having said that, that is one part. But what would you say that in a country like ours, where education is still seen as a vehicle to a better life, to a more financially secure life for majority of us? And
Mhm.
then when I studied abroad, I also saw that the idea that they can explore more also comes from a factor that the socioeconomic structure is such where they are allowed to explore more in their 20s. They have a support system where they can, today maybe they want to explore design, tomorrow they want to combine it with the pilot license. That is well more accepted, probably because our financial structure is very different, honestly. So I
Exactly why people did not want to pursue a career in cricket on the
yeah,
whole. Yeah.
it expands across all sports. If you see, I have a family that's involves professional sports people, and
Wow. Okay.
it's a big risk to tell their future generations that, okay, you're good at sports, you must go for sports. It's not a safe career option in that sense.
So, in fact, Pulila Gopichand actually said that don't pursue sports unless you're filthy rich. He actually went on public record saying that. Sadly speaking, there's an element of truth to it. I have stayed in Australia for 4 years, and it's a primarily sporting nation. And the beauty of being among Australians is that it kind of nudges you very subtly to keep yourselves fit. So imagine I'm living in a house, and I'm sharing the same street with people who are living in other houses and who invariably get up at 4:30 in the morning and go for a run, at some level it's going to influence me to keep myself physically active. You know what I mean? So and by the way, sports is also important. We also come from a generation where, there was this trade-off between evening tuition classes or evening sports. I am actually happy that I kind of belong to a generation where we still got to enjoy those 1.5 hours of evening cricket almost as a daily ritual. And to the extent that, there were points in time when we used to fight with other cricketing playmates for the pitch, for the same pitch. And then to the extent that we also ended up negotiating on, okay, we play from 5 to 6, you play from 6 to 7, or you know what, let us all play together. That will be larger teams and stuff like that. So unfortunately, I think and I see this among some of my students as well. They're very, very sure about what they want to do from a very, very young age. Sometimes when students nowadays walk up to me and ask me immediately at the end of the semester, so what should I do during the summer or the winter breaks? My first response is go on a holiday. Do this to yourself, because you really owe yourself a good holiday. Don't miss out on the time that you have, and to a certain extent, it's okay to be a little uncertain. I was a little uncertain when I had graduated from school, like I shared with you. And it's that uncertainty that led me to take up econ. I would have probably been a happier person, doing mathematics full time. But it's okay. I mean, it was never the end of the world. You see what I'm saying? And embracing uncertainties is kind of essential to living one's life, because nobody's seen the future. And I think it is the scientists who are the best equipped to handle those uncertainties, because there's this latent truth to the field itself. The truth being that not all questions will be answered within our lifetimes. I mean, I do, wonder when I watch some of those movies, DC comics, DC movies or Marvel movies, a fight happening between superheroes and supervillains on the surface of Titan. Will that ever be a reality? Will visiting Titan ever be a reality, to the extent of becoming I don't know, Titan becoming a holiday destination of sorts? And I'm open to the possibility that even if it does become a reality in a somewhat distant future, that future may not involve my existence, and that's okay. Yeah.
That's a very strong motivator, I think. And I wouldn't even say that it's now are the worst times. I think dealing with uncertainties, being that flexible and resilient, they have been essential life skills throughout.
Mm-hmm. Yeah, absolutely. I mean, think of the time when we were troglodytes, being stuck in our caves, engaging in all forms of artwork. But it's that one person who ventured out. That is the one person who is likely to discover new fruits. You know, you know. New places which were probably more habitable than the caves, where everybody hid themselves, possibly from predators. But then, the thing is that a certain level of so at some level, I would say that we are all risk averse, and for a good reason, because there is an evolutionary advantage to being risk averse. Think of a distant ancestor, a mammalian ancestor who is happily munching into the bushes. It hears this sound. Now, that sound could be a gush of wind, a harmless gush of wind, or a lurking predator. Now, there are two competing hypotheses, as we do in statistical inference here. Harmless gush of wind versus a predator. Now, the thing is that, if it's a harmless gush of wind, you continue to munch, you continue to eat food, and that's completely fine. If it's a predator, then you must run immediately. That is also a correct decision. But then the question is, can there be some errors? can there be some errors that we are making? Now, there are two possible errors that we are making here, that we could make here. The first is it's a harmless gush of wind. We assume that it's a predator and we begin running. We begin to run. In which case, we are just running for no reason. So it's a type 1 error that we are making. Or the distant mammalian ancestor was making. On the other hand, a more dangerous error is what is a type 2 error, where you basically you know so the reality is that there is indeed a lurking predator and you continue to eat food. It's game over. That error is a costlier error. So a solution to this problem is what we economists call the minimax solution, which is minimizing the maximum possible loss associated with each possible outcome and action. So, I mean, if you pick up a simple heuristic, like, if you hear the slightest sound, you run immediately, no questions asked, right? Now, what's the worst that could happen? You're just running for no reason. That's the worst that you could be doing, right? And this is called the minimax strategy. When you do not have, when quick decision is of the essence, and you do not have adequate time to react, you look at the predator, you run. You don't think you don't have the time to be contemplative about it. So risk aversion, in fact, has an evolutionary advantage to the extent that it kept a lot of us troglodytes safe within our caves. But then exploration and learning could only happen through those individuals who are willing to take that risk and move beyond the walls or explore the shores of the cosmic ocean in this case here.
Yeah, what a beautifully put argument. Thank you. Thanks a lot. And I think it also helps, like, learning for the sake of learning and developing your skills. It's something even I've noted, like, as a third grader, my mathematics was not the best. Let's just say it took me months and my mother's continuous perseverance to teach me multiplication. I could not multiply or learn how to divide. And so it was very serious concern because I just couldn't. I mean, there was no reason why a child cannot learn to multiply in an entire year. But then I was also learning classical music, Indian classical music, where you have to learn tal. And all of the tal, the rhythmic system, is based on mathematics.
Sure, yeah.
You have to learn it. There is no, in school, you have a choice that if you don't do well in class, well, people are so supportive. In a music class, if you don't do well, that is not an option.
Oh, well. So I'm glad yeah, but you've got a formal training in music, right?
Yes,
so,
yes. Okay. I am still learning. Okay. And that was the reason I managed to learn mathematics, honestly. So from that terrible terror of being terrified of mathematics in third, fourth, fifth, and within 1 year of switch, what really happened was I learned to sing bandishes in proper tal. With tabla and everything. And what that happened was my mathematics score was 100 in 6th standard, 100 out of 100. It was magic. And it was nothing had improved in my the school side of things. It's just you learn things differently. People learn things from various sources.
Yeah. Well, to give you a very quick example, if you were to look at Fibonacci numbers, also known as Himchandra numbers. So the idea being that you kind of add two numbers to get to the next number. Every number in the sequence is basically the sum of the previous two numbers. And in Indian classical music, a direct application of it is if you're trying to cover, let's say, an 8-period beat count as a sum of ones and twos. One beat and two beat, a beat that lasts for two, or a so one beat and two beats. In how many ways could you fill up all the 8 spaces? And the answer is that it's the 8th Fibonacci number, for a very obvious reason. The proof is very elegant. I mean, think of the last space. It could be either a 1 beat or a 2 beat space. Now, the thing is that if it's a 1 beat space, then the initial 7 spaces could have been filled up in, let's say, F7 number of ways. And if the last space is a 2 beat count, then the initial 6 spaces would have been filled up in, let's say, F6 number of ways. So F8 has to be the sum of F7 plus F6, which is essentially the Fibonacci rule. So in Indian classical, yes, in Indian classical music, yes, in fact, there are these pieces where, so I, back in my undergraduate days, I used to be the convener of the music society, and we actually tried out these experiments where, we had these eight beat counts, which are very, very common in Indian and Western music, and we tried to use different bowls on the tabla, different rhythmic patterns on the tabla, and exhaust all the different Fibonacci patterns that allowed for filling up those eight spaces. So yeah.
Wow, that's brilliant to know. Thank you, Professor Banerjee. It has been an exceptional episode today.
No, thank you for having me. I've enjoyed this as much as you have, probably more than you have enjoyed it. So
thank you. That's very kind of you, because this podcast is meant for, it's not just for space professionals who are in the industry to tell us, okay, this is how. They probably even can't tell us if they're working in a company, which they won't allow them to tell it. There are a lot of restrictions, but it's for people to understand that things are multidisciplinary. There are transferable skills. And
yes, absolutely. I totally agree with you. In fact, when it comes to my PhD students, I do ask them to, in fact, force them to read what's happening outside of economics. The top five journal articles, the top five journals in economics, of course, they keep a track of it judiciously. But then I do occasionally ask them to read, something that gets published in Nature or Science here and there, just to, and I don't, again, force my students to, understand everything right down to the last detail, but I do encourage them to at least know what is happening. And that to me is enough.
Thank you. Thank you so much. It has been lovely. And to everyone watching, please let us know if you like this episode, and also check the link in the description. There will be one link to tell you where you can find more educational resources in space. And Professor Banerjee, I'm incredibly grateful for this episode today.
Thank you for having me. I'm also incredibly grateful to you.